All right. Go ahead.
All right. Good evening, everyone, and welcome to our after hours. So today we have like three major stuff we want to talk about, and that's just sort of a brush up of the basics in Python. Talk a little bit on linked lists, and then would talk on binary search trees. So my initial intention this evening was really to sort of walk us through the basics of Python classes, what it entails, talk about the init, talk about the str method, talk about the repr method and all that. Yeah. But I realized that if I start doing all of that, I'll just be repeating every single thing in the training kit. So apparently, day 3 of the training kit sort of goes very much in depth about Python classes. It starts from the theory of like understanding the concepts behind objects and models and blueprints and all of that. So it talks about encapsulation, inheritance, polymorphism, abstraction, what they're all about. And then it now goes further to talk about objects and then talks about classes, how classes are supposed to be declared, talks about attributes and methods. And I feel like if we actually settle down, take some time out, I spent like the last hour going through this on my own. And I feel like if we actually settle down and take out like an hour or two to really look into this part of the training kit, we'll understand the deep things in classes for Python. Yeah. So there's a lot of things here. The first example that they gave here was about, I think, users, products, and purchases. Yeah. And it takes time to actually break down these examples, define the classes, and every single thing that is being used. The reason why we have the self in our init, the reason why we have the self in our init, the reason why, for example, we have is admin is declared as false, and a lot of things are explained, and like the reasons why they're being used is explained here, and it's very, very deep. So I feel like I'm going to drop the link in the channel, yeah, so that just in case we missed it, I feel like we should just get back to the training kit and go through this. And subsequently, it's very important that before every lecture we go through the training kit. It helps a lot, because looking at this now with all this information here now, I see no reason why Tom would have to go through all of this again in class when you already have access to this. So he would have to move further ahead and assume that you've gone through this. And when you've not gone through this, you obviously be lost in class. So that's for classes in Python. I'm going to share this link in the channel, and I'd advise we all go through it over the weekend to sort of have a solid understanding of it. Then talking about linked lists, I don't know how many of us were present on Tuesday when we talked about linked lists, but I think I tried to give my own perspective of what I understand by linked lists. It may not have been perfect, but I know having different people talk about the same thing gives you different perspective and makes you to understand stuff better. Yeah. So I shared, I think, 2 videos on the help channel this morning during lectures. I don't know how many of us saw that. I know that some of us did, because like we sort of like reacted on that. So I'm going to bring it back down again. And I would say there are 2 videos. One is from an instructor in HackerRank, and then the second one is from CS Dojo. So like I was going through a lot of linked list videos, and those were the like 2 best short videos of linked lists that I saw. So I would also say we take out time, and the 2 of them all together, they don't round up to 30 minutes, I guess. So we'll take out the time also to look at those videos and would understand the concepts. The beautiful thing about it is they spend more time explaining the concept behind linked lists rather than writing the code. So they just did a little bit of the code towards the end, but they try to explain the concept behind linked lists, talk about the node, talk about the pointers, talk about the head, the tail, the previous, the next, and all of that, depending if we're talking about doubly linked list or singly linked list. Okay, so I would say for the linked list as well, if you missed our Tuesday after hours, the video is up like a little bit on top in the after hours channel. So you could just go through that portion of the video. And if that is not sufficient, you can also go through these videos that I'm going to also share about linked list. And I think like it will give you a stronger background about the underlying concept behind it. Then you'll be able to understand and figure out how to, create the methods that you need, methods to add to head, remove from head, add to tail, remove from tail, and resize and all of that. Yeah. So like that's just what I needed you guys to know about like those two. So Malky will talk about the binary search tree and perhaps take an example with us. Yeah.
Yeah. Yeah, thank you. So again, now would be the time for any questions you have on either linked lists, basics of Python, anything you don't understand right now that you think you should. Basically, any type of difficulty you've been having lately. So anyone?
My main confusion is just like really the methods, kind of the logic in the methods, like, and really it's not even the logic, it's knowing what is, like, say self, or like I know what self is, but like the other parameters that come into the methods, knowing what they refer to and what they're supposed to do, if that makes sense. Like there'll be like self and then value or target or left or right or whatever, or even knowing how left, like why is left left? How do we set left to be what's on the left? Because like I always think of like kind of arrays. I think I'm associated all too much with JavaScript arrays and been like indexing them and like incrementing them or decrementing them. But I mean, because there's no definite way to like scale up or down on an index, it's hard to kind of visualize how it's going left or how it's going right. If that makes sense.
Yeah, let's go over that then. Let me see, just share my screen. So what you're looking at right now is the definition of one node. It's not specifically tied to anything right now. No linked lists, no anything. Okay, so but I don't know what you prefer. Do you prefer just that or just going straight into the linked list itself?
Say it again, sorry.
So do you want to look at a definition of just one node in a linked list, or going straight into the implementation of that list?
Yeah, maybe go through the node, because I suppose you need to fully understand the node before you can understand the list. And okay. Maybe I don't understand.
Yeah, okay. So let's get started with the simple stuff, right? So first we have the class definition, right? Then we have the init method for which is basically the constructor. And what does that mean? It's basically a way that you can replicate all this stuff, all these properties and all these methods in any number of objects you want. So if you want to make a ton of nodes, you can just call this class anywhere and pass any of the parameters that you want to pass, right? So this would be how you create a node. And obviously, well, now you can see that this init, right? To construct a node, you kind of need at least a value because the other ones here, they have default values. So they start at none technically, but you can also pass something if you want. Does that make sense? So, and the self here, yeah, it's not considered.
Sorry, Melky, I was muted. You were saying the default values start at 1.
At none, sorry.
At none, okay.
So
because you set them, or just
if you it's a default value. That's it's written here. So what this means is if I don't say anything when creating the node, it will set the previous and the next to none. So it's not connected to anything else if you don't do it yourself. Okay, so it will not connect to anything. This node, if I create a node with a value of 1, sorry, let me place it below here. Okay, so if I create this node with a value of 1, technically what happened was this init ran, it just ran and set my node, right, dot value to 1, set my node dot prev to none here, which is the default, and the next as well, because I didn't specify the other arguments, okay? But if I did, so imagine if I had, I don't know, the previous node, right? It was another node somewhere that I created with the 2, and maybe I also created the next node with the 3. Okay, so if I had this, I could just directly place them here and already construct this new node here with the right connections right from the start. Does that make sense? So yeah, was that clear? Did I answer your question?
Yes, thank you.
Oh, right, I couldn't see you there, you know, in the dark.
Oh, I'm here hiding.
Okay, okay. So is it also clear that when you create a node, technically it has the same exact properties that you would attribute to the self, right? And the same exact methods as this class has. Like all of these variables, they have those properties like the value, the prev, the next, right? And they have the delete
because
method.
they're essentially list node.
Exactly, they're a new instance. So a new object is like you're just creating a new. So in JavaScript, you usually would say something like, I don't know, you could say this const array, new array, which would technically be the same as just creating this. But yeah, here you're using the class and here you're not. But again, it's just a new thing, right? And the classes help you basically set a, well, write down a set of instructions that all these objects will follow. And in this case, they're nodes, right? It could be anything really, right? It could be cars. It could just create a class that makes cars, and each car has a bunch of properties like the fabric speed, the model, the whole thing, right? So instead of you coding a bunch of objects like this, like car 1, and then you like start writing down for each car, you have to type down like a bunch of properties, and then you need a second car, and then you need to write all of this again. Okay, classes kind of take that problem away, and you can just call car and code it once up there. Okay. So yeah, do you wanna move on to? I kind of forgot the second part of your question there. So you talked about what the arguments are for, and then
yeah, I was just really kind of confused about how something is set, but I mean you're setting it you're kind of manually setting the previous and the next. Like yeah, that makes sense now. Not manual. Well, yeah, you are manually setting, like in the initialization or in each stage, you're setting you're passing in values that are previous, that are next, and they sort of, yeah.
They become well, they will be stored in.
Because I kind of thought that the method would have to kind of figure out itself what was next and what was left and what was right, but you're already telling it when you call the class. So
well, I think you're talking about when this happens, right? You're talking about when there's no option, right? But
yeah,
there's no option to connect right up front. Okay, so that doesn't mean that you can't change it afterwards. Okay, so you can still change it even though you cannot do it up front when you create it. Okay, so if I went here and said that my new node dot I don't know, next is now the previous node, it changes. Okay, so it doesn't need to have arguments. Of course, well, in my opinion, I don't know, yeah, the default is none, so you can kind of set them here and allow the user to like use your class and do things directly. But it could also have like a new method called set next or something, and then it receives the next, and you set it here, and you do self.next equals next from the argument. Okay, so you could also do this. So there's various ways to change the values of these properties. I think you've also seen before that you can actually just also change the methods themselves by overriding them in another class, right? So
what do you mean by that? That sounds confusing.
It's not. So if, for example, if I have another class, which this probably is not applicable, but let's call it sublist node or something, that inherits from the node itself. Okay, so I don't know, maybe this node needs a different thing to work. Let me see. Let me just type out the constructor here. And the only thing different in this node is that it has a speed, so it moves, and in this case self.speed is the speed, right? I think I do need to call super here or something. Oh yeah, I think it needs the value. Yeah, it needs all of it to work, I believe. But yeah, so if I did this, initialize the value. So this subnode is when it is created, it will ask you for a value and the speed now, right? And the only thing difference about it is that it has this new property. But if I wanted it to not delete the same way as this one does, right? I could just override this and say anything here, anything else here. Like for example, um, doing self.speed equals 0 before deleting. Okay. Does that make any sense?
Yeah, it does. You're specifying what the kind of parameters will be
I'm saying,
inside a method.
Yeah, I'm saying that I can technically override a method if I give it the same name here, right? So
yeah,
this class is inheriting from this normal node. So technically it comes with all of this stuff here already. So it comes with all of this, all of these functions here, okay, sorry, methods, right? So my sublist node has the access. So let me just call this a new thing, subnode, right? It has the access to this node, this method here, insert before, which is from the parent, right? So I could just do this, right? Insert before, and it actually auto-completes, so you can actually see that even VS Code detected that it does inherit, okay? But if I wanted to change how it works, right, and I redeclare it in my own class, it will call this one instead and not that one from the parent. Okay, so that's just effectively overriding the delete method and creating a new one, right? Just changing how it works. Okay.
Yeah.
So
thanks.
Is there anything else here that doesn't seem too obvious?
Well, could you just scroll up a little bit? Like, say, on line 17. So the method is getting self and a value. So how does it know what self.next is? Is there different? Okay, no, I kind of get it. Self has like the equivalent of an initialization, everything that's there. So it has value, previous, and next. And you're just saying that self.next is current.next. Yeah, I get that actually. Sorry.
So yeah, exactly. Yeah.
Like self, like you can have self. This actually sounds, as I say it, I feel like I'm sounding stupid, but I mean, there's different like self.value, self.previous, and self.next come in on self, and then you can access whatever you want and set it to something else. So yeah,
yes. So you have the properties.
Yeah.
They don't change unless you do so. So and the self that you're referring to, this is like it's kind of a keyword. So it comes from where you call it. So if I do new node equals this one number 1, okay, so it has the value of 1, and I call it like this, insert after 1, right? The self is technically the new node object here. So like it's my new node variable. Okay. So because it is a method, does that make sense?
Yeah, it does. Thank you. Yeah.
Okay. So and again, like you just need to pass the arguments that are after the self. So no need to have 2 arguments here, just the value. And yeah. because the self comes from here.
Thanks a lot.
All right. So anyone else has
Yes.
questions?
Can you explain the code from line 17 to line 21? Because I'm
Yes.
seeing that the pseudocode from line 13 to 15 is only 3 lines. How you can explain the code that you write from 17 to 21? What actually is doing?
Okay. So it says wrap the given value in a list node and insert it after this node. So wrap the given value, that's this, the arguments, right? That's what you're given in a list node. So I'm assuming now that I need to use this class with this value, right? So that would be this part here. And insert it after this node. So after is the next, right? So we have the self next equals this new value, this new node with this value, right? Note that this node could already have a next node it is pointing to. Okay. So this second part is a warning for you to be careful. So if my current node that I'm trying to insert something after has already something after, so if I had a node with the number 1 connected to a node with number 2, right? And I call the node with number 1 insert after number 4 or 5. Okay, so if I call this on the node with the number 1, I already have the number 2 there, so that's a problem, right? So what it does is it first saves it, so saves the number 2 in a variable here. Sorry, the node, not the number. When I say number, I'm talking about the nodes. Okay, so it saves it first, then it reassigns it. So it actually places the 5 there. So it saves it on a variable. So now the number 2 is equal to the current next, and then it reassigns this. So now the next of 1 is 5. Because the given value was 5, okay, and then it also connects backwards and forwards. So it connects to the self. So this is the previous, as you can see here up top. First comes the previous, and then comes the next, right? So it connects to the previous, which is the number 1. Okay, connects the 5 to the number 1. And also the 5 to the current next, which is number 2, okay, which was there before. All right. So what's the only thing left? The only thing left is making sure that the number 2 connects back to 5. So it does this. Sorry, it should probably be like double arrow or something, because it goes back and forth. It goes previous and next, right? So did that make sense?
Okay, thank you.
Did it make sense?
Yeah, it's okay. It made some sense. Yeah.
So yeah, it places the given value here. So it places some number in between in between these two numbers that were here before, right? Before you just had this with 1, 2, 3. But if you want to insert the number 5 after the number 1, you kind of have to reconnect both the number 1, the number 2, and the number 5 that comes in. Okay, so you kind of have to connect all of these things like this. Okay. So yeah. Anyone else? Any other questions about the nodes or linked lists or anything before we move on? All right, I'm gonna assume that there's no questions, but if you think of anything, just let me know. So the other thing we have for today is just talking about binary trees. So this kind of needs to be a group effort from you because since this is kind of a afternoon project, I can't just go ahead and code everything up for you. But we can code it together and talk about why things work that way. Okay, so I will ask you just to participate as much as you can, but technically the less people participate, the less people learn anything. So this kind of depends on you. So I'm just gonna go ahead and declare my class here. And we should, so I'm just gonna go and place some functions that we should try to implement. And then we can go over those, okay? We do have a code challenge with this after. Just to reiterate, but for now, we can try these methods here. There's a lot more, but yeah, it kind of depends on you. So let's go. Who wants to take a stab at the init? I'm sure you guys have some idea.
Okay, let's start self dot value.
Okay.
Is equal with value.
All right. A good start. So this is where you're gonna save the data. What else?
I think because it's a binary tree, you need to have the left side and the right side. So you have the self dot left, and then you have the self dot right also. So that equals left and that equals right.
Sorry, that equals what?
Self dot left equals left, self dot right equals right.
Yeah, and where do these come from?
So I think we can actually initialize it in line 4 there, pass it in as an argument and set it to null.
Okay. Like this?
Yes.
All right, so we have the init done. Insert. So the insert is supposed to add a new node to the tree, okay? Just in the correct place. So anyone?
Yeah, for the inserts, we can either insert to the left and to the right, because on a binary tree, the minimum values are on the left and those on the right are the maximum values.
So do you have any idea how to do that?
What we want to do is, we since we are passing in a value, we have to compare that our value with the root value that we have, which is our self.value. Now, if the value is less than our self.value, it obviously goes to the left. If it is greater than our self.value, it goes to the right. So we are going to have like an if else statement in the method there. So we try to compare if value is less than self.value. So that means we are moving to the left. We can actually do less than or equal to. Yeah, so it could be equal to also. So if it's less than or equal to the self.value, that means we are going left. And then, so what we also have to do is we also have to check if we actually have, if we have a node on the left side of our root node. So we have to do like if there is no self dot left. So if self dot left is none. So that means there is no self dot left, and then we have to create a node that will be there. So our self dot left now will now be equal to a new node that we are going to create. So it's going to be binary search tree invoked, and then we pass in value.
Okay, so let's just pause here. Does everyone understand the code so far?
Yeah, it's like a filter saying if the value is less than the current node's value,
Okay.
do this. If not, do something else.
And then, is this clear why we're checking?
Why we didn't, so in line 15, sorry for interrupting. In line 15, we are examining if the value, if the argument, whatever ni number we are choosing, it's less than equal of the actually node, actually tree, correct? Is that what we're examining?
Yes.
So in line 16, why we didn't say, is we said if self.left is none, so if the actually tree on the left side is none,
yeah.
And then we set this, and in line 18, we set the left node, the left tree, the left actually, in the binary search tree value. My point is, why we didn't say in 17, if not self.left, and we said if self.left is none.
Yeah. So if not self.left is just another way to do the same thing. Okay. So for example, you know that this is a node. Self.left is just one node. Okay. And if it is empty, it will be none. Isn't that right? But technically, none is a falsy value. It's what you consider as something that if you compare it and use it as a boolean, it will be equivalent as false. Does that make sense? So what we're trying to check here is if the left is actually empty, then this will be true. This condition will be true, right? And the other way this works is with the not, right? Which does the exact same thing, but it does it differently, right? Instead of checking if the left is none, it checks if not self left. So what this does is consider none as false, right? So if that was false, we wouldn't be able to come in here in this if statement, right? Because that's how if statements work, right? Only if the condition is true is that we go up down here, right? So we do a not, so it inverts the false into a true, right? It just inverts the value from whatever Boolean it was before. If it was false, it goes to true. If it was true, it goes to false. Okay. So because when we have the empty node here, we'll have a none, and the none is equivalent to false. Not false is true. Does that make sense? So that's it. They're exactly the same. I personally like more this one, which is more, it's both more readable and easier to understand than the other one, which you kind of have to know the concept of falsy values to do that. Okay. So is there any other questions so far? Okay, so let's continue with this method. What's left? Who was speaking?
Okay, I was the one.
Okay.
So we have actually looked at if there is no self.left. Now we have the else block now, and then here now we are going to basically say our self.left, and then we are going to insert the value into the self.left, since this is the reverse of the if block. So self.left dot insert, so call the insert method there, and then we'll pass in the value.
And sorry, why is that?
We are actually doing this because that means we have a node on the left side of our root node, and then we need to give the value. That's why we are doing line 22. I don't know if my explanation makes any sense.
Yeah, it made sense, kind of. So do you know about recursive calls?
Yeah.
Okay, so as I have explained before with just the node class, right? Any node that you're going to have will have the same exact methods, and that doesn't become different when you reach the binary trees. Okay, so your self.left is just another node, but it goes to the left of this node. Okay, it's just that. So this node also has the insert method that we're typing right now. So what happens when I call this? What changes that makes the program go forward and not go into infinite loop? This is for anyone, by the way. So yeah, what changes? What changes when I do this? Yeah. Okay, so
I'm not sure I understand the question.
Yeah, can you repeat it, Melky?
Okay, so the question is, why are we doing self.left.insert, and what changes? Like what is the progress to resolve the insert here? What happens that makes this eventually stop running and insert our node in the correct place? What changes when you do self.left.insert?
Isn't it because okay.
You're saying, does it means that he has reached the would I say the last node on the left?
Well, I know that when it reaches the last node on the left, it will eventually go to this if statement and say that is none, and that's what you mean, right?
Yeah.
But what makes it go all the way down? Why is it progressing here? I just really want you to figure out what's the difference when you're calling insert.
Because there is nothing, there is not another, there is not, it's progressing in the left side because we are asking the whole time when we have a new node, when we have a new argument, we are asking the whole time to the node. This is if example 3 is less than 5 is less. We continue. The next node we found there a node 4. We cannot put there. We continue on the left.
Mm-hmm.
We are asking again. 3 is less than 4. Is 4 is less than 4. We continue to the left side because we know that the left side has less value numbers.
So that's exactly right. So what changed? What made the code know that? What changed here when the next call of inserts? What made it know that you're now talking about the 4 instead of the 5? Because I think that was one of the questions from Owen as well. So I'll just give it to you, but this is the important part. Okay, so what changed was the object, right? The context. Okay, the self. This is what changed, right? You're on a node, which is the self, but there's another node to the left. So you go left and you try to insert it there because this node you cannot. Does that make sense? The self changed. So now you're technically at the second time this runs. This self here is a new node and it is the node to the left of the root. Okay, and that's the progress. This is how it knows that now the value is 4 instead of 5 because we called it from here, from the left node. And now the self here at the second call is this left node. Okay.
Yeah. Can we traverse the element on the left node by saying, like on line 22 now, we could actually say our new self will now be equal to self.left, something like that, and then we come back to line 23 and say self.insert. Am I making sense?
I think so. Yes, I think so. I think it will work doing this. This is what you mean. Self.left and then self.insert.
Yes.
I think it will work. However, it looks weird to me for some reason. Assigning the self, I don't know, just looks strange.
Also, you might get like a referential issue down the line, and it could cause other problems because it's a like a keyword for this object. You're saying, I want this object to not be an object anymore. I want it to be a pointer to another object as well. In this instance, you can't make anything, and it should be fine. But in most circumstances, it's a no-go to do that. If you just don't.
Okay, is the problem actually with the name we are giving the container, or it's just that it's wrong to do this?
All the problems. It's just because we're calling it self, and it's like a reserved word.
Okay, so we could actually say new self equals self.left, and then we come back and say new self.insert.
Yeah.
Yeah, if
Okay.
you called it any variable name, it works fine. Yeah, but reassigning the self is not so good. Okay, so okay, so that's how it works with recursion, right? It progresses. It keeps doing progress by changing the context on where you call insert. Okay, it changes the object, the node itself. So
Yeah, one question. So at what point does the node change? What line? 23?
it changes when this is called, and what happens is this insert at the first time was called, let me draw, so I guess it's the best way to describe. So if I have a 5, and I'm just going to complicate it a bit, so 4 here, okay, and we try to add a 3 like the example demo said. So the first time this runs, your self thing here, it's probably 5 because it's the root. Okay, so you're gonna start here. You're gonna check. You're gonna see that it does need to go to the left, but there's already something there, so it goes up down here.
Okay. Okay.
And what happens now is, let's call insert on the left node instead, because this node we cannot insert anything. It's already filled out,
Okay.
right?
Okay.
So
okay.
what
Makes
happens
sense.
next is a new call to insert starts, and now the self is the node with the 4. And now when we reach here, you have the 4 instead of 5, and etc. Right? Self left is no longer the 4 like it was before. It's trying to see this connection right here with a new error here, but there's nothing. So it is none. Then create a new one. So 3. Okay. So as you can probably tell, recursion is just another way to loop over code. Okay, it just does this back from the top of the function. Okay. Did that make sense?
Yeah.
So
Makes sense.
the self, which is the object in our drawing example, was the first time was 5, the second time was 4, and so on until it will find the way to put the node in the number in the new node. Is that correct?
Yes.
Oh, got it.
Yeah, we keep changing until it finds a place. Okay. So yeah, the rest of this, I'm just gonna save you the trouble because it's the same logic, so there's no point, I guess. So let me just do an else here and do it for the right side, which is just a copy paste and changing this to right. Okay. Because if the value is not less or equal, then it is bigger, which it means it goes to the right side. Okay, and the logic is the same. It just calls it if the right side is already filled out with the node. It calls it again on by going right, and if it's not, then we create the node there. Okay. So yeah, we have the insert done. That's it, right? Anything else? Any other questions? All right, so let's move on to the contains. Who wants to do this one?
I could. So first, so I'm assuming target is is the value you want to check to see if it's in the tree, right?
Yeah, it's kind of a search, yes.
Yeah, so
Sorry, Alex. Target might be also an argument, a value, a number.
yeah.
Yeah, it can be anything really. It just depends on what does your tree hold right now. Is it numbers? Is it strings? Right. It just depends on what you're trying to search for and what data is already in there. Right. Of course, if you have a binary tree of strings and you search for a number, it probably won't find anything. But that's the goal. It needs to know that it didn't find it. Okay. So yeah, this is like something that returns true if it finds a node.
False if the
Node with a value equal to target. Okay, so that's it. That's all this does. Okay. So what's the idea here?
so we know that self is the current node that we are on. So we want to check to see if the target is the same, has the same value as self.value, as the value of self.
Okay, let's start with that. So
if target is equal to self.value, we want to return true. So I feel like the next thing we need to do, obviously, is to find a way to recursively loop it to meet this whenever it's false.
yeah,
Obviously, we would need to check again to see the side. So we need to check to see if the target is greater than the value, right? Then we move to the right. Then if it's lower, we move to the left. So we'll do if the,
and why are you doing that?
because the values on the right are obviously going to be higher, and the values on the left are going to be lower.
Exactly. So there are preset rules for this data structure. So you already know where where ideally a value would be based on what you know about the rules of this. So if the target is less than the value of this node, then you need to go left, right?
Yeah.
Okay. So
left.
All right. And what's next?
Here we obviously need to check if there is a node on the left. So check if self.left exists. If self.left. If it does, we'll need to run the contains again. So we need to loop back to the top. So it'll be self.left contains value. Targets rather, not value.
All right, like this.
And if it doesn't, we want to return false, because obviously that's the last node, and if it doesn't find it there, it means it doesn't exist.
Okay, so any questions so far for the others? Anyone? I think you're beginning to see a pattern, I hope, at least.
Yeah.
So if you look at this, and you look at how this is becoming right now, there's not much difference, and the logic is always the same. You have a value that is less, so you go left, and now then you're going to have a value that is right, so you go right, that is higher, so you go right. Okay, so I'm just going to copy paste and change this to right side.
That works.
So we examine in which side the value will go in line so if it is less, it will go in the left side. If it is greater, it will go to the right side.
Well, saying that it will go seems like you're trying to insert. What we're talking about is it will continue searching, but only for that side. Okay, so because we're searching, we have two main values to compare with, which is like with any kind of search, right? You're searching for something which is, first you have something that the user typed, which is the target, something the user wants to search by. So let's say he wants to search the number 3, and you have a binary tree starting here. And it starts with a 10. And the rules are stuff that is less goes left and stuff that is more goes right. So technically, you've already eliminated the whole right side just by knowing this rule. Okay, imagine there were like 1 million nodes for each side of this tree. Like, yeah, it's pretty big difference, right? So this side has been completely cut off right now based on the code that you just that was typed here. So first we're checking if our node here is our value that we're looking for. It's not, but yeah, we should check, right? So it's not, so we check, is it less? Then we go left. It is, so we go here and we check if we have a node there, we can call contains again, because again, all the nodes have the same exact methods and properties. And okay, so you can just move on to the left, and now your self has changed from the node with the number 10 to any other node that was here. I don't know, maybe 9. Okay. And it just keeps doing this until it finds the right spot. So obviously, if at some time, I don't know, maybe next node was like 2, right? You could have this happen where it has the 2, and then at some point it will stop, it will reach this node here, and it will check that the target is actually higher than the one I have right now. So that's why this else is 4, and we go right instead.
Yeah.
Right.
Yeah.
And we place it here.
I got it.
Well, we try to find it here, not place it. We try to see, and this is called on the right side. And when it comes back up, our new node is now the 3, and then we found it, right? Because we have this code right here at the start that tries to see if we found it each time, right? Basically, each time this code passes a node, it tries to check if it is the actual value that we're looking for. Okay. So that's the general overview of this. I see, well, yeah, I don't know. Is there any other questions about this? It's very similar to the inserts. But yeah.
Yeah, I think I'm still a bit confused on
Hmm.
why we are doing self.write.contains self.write.insert. I want to ask, can we actually traverse what we have on the left or on the right with a while loop?
Yes, we can. So what we're doing here is what you call a recursive solution. So what that means is just the function calls itself. Okay, that's basically what it means. And it technically is a loop if you think about it. Okay, but you can also do it with the while loop. Okay, with the while loop, it would be different. So let me try that. Let's see. So I think I would need some kind of place to keep track of my current node. Okay. And I'll start with self. Okay. And then I'll just place everything I have here inside this while loop. And I'm gonna keep checking until my current is not none. So, sorry, until my current is none. Sorry. If we reach a point where there's nothing left there, it just stops. But okay, so then I'll be checking if I've reached my target, return true, that's fine. If the target is less than this node, and if we have a node to the left, then we need to change the node, right? So how would I do that? Any ideas?
So car will probably be self.left.
Yeah. So changing it like this makes it so that the next time this loop runs, sorry about this. It's probably not like this. It should be, everything should be kind of curved. Because it needs to be updated, right? When I change it, it needs to change on the next loop. Okay,
Yeah.
so yeah, sorry about that. So the self is just use that to start, just to.
Yeah, but is self not changing as well?
No,
Okay.
just
Okay.
the variable that I just created.
Okay.
Self only changes if the method is called again. No?
Yeah, yeah.
Like there has to be a loop for self to change each time, I think.
Yeah, I feel like self will only change when it's recursion, right?
Yes.
Okay.
That's exactly right. Yeah. If you call the method like this, you're calling it basically anything that's behind it is yourself. Like it's your object that you just called contains on. So that is it. This self here is not gonna be changed at any time. We didn't do the right side yet, but we will. So I think this is fine. Let me see. So it goes further left, else false. Okay, I think, yeah, I think so. And then goes right. So right side is just, again, same thing, but instead right. Okay, so let me just see. The only thing I'm concerned is when this changes, it cannot do anything else, but I think it doesn't do anything else. So I don't know if continue is a keyword or something, but we could use that. But for now, I'll just not do it. So if you think about this, it's fairly similar, but it's an iterative solution. It's not, the function is not calling itself now. and we're using the while loop like you were asking about. Is it clear how this works?
Yes, I think it is clearer now.
Although I think that once I reassign this and this becomes none, it will not return the false. So I will return false at the end of the loop. Okay. Was that clear? So I don't know if no, yeah, it doesn't make sense. Sorry. Yeah, never mind. It does the check right here, so it doesn't need to. So okay. Any other questions? Let me actually copy, do some things backwards. Okay. And I'm gonna place it right down here. Okay. And call it iterative. Okay. All right. And we have the get max and the for each. Do you guys want to move on to BFT, so breadth first and depth first? Because I'm saying this because these two here, there's just more of this. Okay, there's just more of this. It's kind of the same logic. You could do it recursively as well, or iteratively. Okay. What do you want to do? Move on or do these ones really fast and move on?
Let's do also the PFT and DFT and whatever.
Yeah, I mean, I would say we should move on because I kind of already get the idea of all these.
Same here.
All right. We have, I don't know, 3 out of 4 out of 5. Okay. All right. So let's move on. All right. Let's try to do BFT and DFT. So let me, yeah, not this one. Like this is what I meant to do. Okay.
What is B?
B is breadth first. We'll go over that. Let me just
because in the morning I didn't understand what was B, and I was having I had breakfast. Say about breakfast, about food. It's okay, I'm here. Sorry, Tom, I didn't hear the the word in the morning.
Actually, a breakfast traversal sounds really good, actually. Just have lots of different breakfasts.
All right. So, yeah, exactly. So breadth first is the concept of traversing the list like this. So let me draw again. All right. So I'm gonna just draw a very basic thing. So I'll start with a 10 here, 15 here, like, oh, that's pretty bad. Okay, so 8. Okay, let's say this 8 have a 9, and this 15 have a 14. Okay, so I think this is good to test. That's a 20, by the way. So, okay, breadth first, right? Let me draw it in a different color. So the way breadth first works is side to side. Go over those nodes side to side. So the whole tree, but from side to side. So it goes this level right here, and then it does this level right here, and then it does this level right here. So it goes 10, and then 8, 15, and then 9, 14, 20. Okay. So that's breadth first. It goes level by level, you could say it, or side by side, side to side. Okay, makes sense? Depth first. Depth first is sort of an opposite. So, oh, I cleared my tree. That wasn't the goal. Okay, depth first is the opposite. So instead of going like this and then this and then this, right? It does first goes down to fully until the end, and then it keeps going down until it can, and it comes back up and goes down until the end, right? So it goes from top to bottom first, and instead of side to side first. Okay, so it's a it's kind of an opposite, you could say. Okay, is that clear to everyone?
This is the depth first.
Depth.
The depth
So,
goes from to bottom.
Top to bottom, yeah.
Top to
So
bottom,
it traverses
okay.
all the nodes from the top one. So you could say like this. I'm just gonna draw it again. Doesn't matter. Okay. Okay. So it goes from this first one here, goes all the way down until this one, and then it doesn't find anything else because this one doesn't have any connections right now. So it comes back up, and then it would go all the way down on this side right now. So it would go here, and then it would come back up when it didn't find anything else, and it would go all the way down, back down. Okay, so it goes top to bottom, and the breadth first is side to side, level by level. All right. Hope that was clear. All right. So, and the thing with breadth first and depth first is that for one of those we use a queue, and the other one we use a stack. Anyone know which one it is? Which one does what?
The queue is first in, first out, and the stack is last in, first out.
Exactly. Yeah, let me just. That's exactly right. So which one applies best to a certain type of traversal? So think of breadth first. Let's try breadth first. So I'm gonna draw a tree again, and this time it's green because okay. Which one would apply best if you want to try to traverse these nodes based on this order right here? So it goes 1, 2. Well, I can't place a 2 there, but yeah, it just goes the root, and then the left, and then the right. So it goes level by level. Which one would apply best? So I don't know, maybe.
I think the queue would be for the breadth first, while the stack would be for the depth first.
And why is that?
Looking at what you just sketched now, so we are moving side by side. Mm-hmm. And the first that is passed is, if you look at it, let's say we have 5 and 7, or let's say we have 3, 5, 7. So if you are going to take it out, you're coming from the top, which is the first element there. So that one goes out. then you go next to this one. So it's actually that first come first serve basis, so which is first in first out.
Okay. I don't know, makes sense to me. Does it make sense to everyone? So the queue would apply to the breadth first, and that's because exactly that. So when you're on a node, you queue up the 3 and queue up the 7, and then they come out in the right order. Does that make sense? So if you're on 5, right, and you queue up 3 and 7, what comes out is 3 and 7. Does that make sense?
Do you queue up 5 as well?
Yes. Yeah, that's the starting point.
Okay.
The queue already will start with the 5 because it's the root. So it needs that to go somewhere. But yes, it will be on the queue. So of course it will queue up 5 to begin with, and then it's gonna try to check the left and the right. So in my case, I don't know if it is optional to do it left to right or right to left. I think it is left to right though, usually. So yes, so you queue up 5 and then you queue up the left, queue up the right, okay? And what comes out is actually 5, 3, and 7 because it's first in, first out. So you queue up 5, 3, 7. What was queued up first was 5, so it comes out, comes out, comes out. Okay, so it makes sense. Does everyone get it? And now, of course, obviously the stack goes into depth first. Okay. And the reason is, again, like the way the stack works will really be compatible with going down and then coming back up, because the order is a bit different, right? So let me see. So start with a 10 here, 9, 8, 7. Okay. So if you go a depth first, it will do something like this, all the way down, and it will push onto the stack 10, 9, 8, 8. Okay, that's bad. Bad typing there. Okay, 9, 8, 7. Okay, it will stack up like this. Okay, so last in, first out. What comes out first? So it prints 7. Okay, the last thing that was placed comes first out. Okay, so last in, first out. So the 7 was the last in, so it's the first out. So it goes 7, 8, 9, 10. Okay, so it will like print exactly like that, 7, 8, 9, 10, because it is doing the stack. So if it was a queue, it would print 10, 9, 8, 7. Okay. All right. Is that clear?
Yeah.
All right. So let's move on to the code examples. I still have the code challenge to discuss, and let's see if we have time for that. Okay. So let's start. Which one we want to start with first? You have a volunteer for breadth first. I'm gonna give you tips this time because these ones are harder. So let's see.
Sure, I could volunteer for birds first.
All right. So first thing that you can think of. So you're receiving some tree. This is the root of the tree, the node here. Could call it root. Doesn't matter. You're receiving that tree, and you wanna know, like you want to print the whole tree red first style. So let's do this. First thing you need to check is what?
We need to check. I mean, first of all, we need to put the node, the root in a queue, right? So.
So start up the queue.
Yeah.
I don't know if you want it like this or like this, but yeah. And then you want to add it.
Yeah. So we need to put the queue. Self is the node. Or is that roots? I'm not sure.
In this case, we're not printing the node from the self. We're printing from this one that we receive. Okay. I see the confusion, but we're ignoring this.
So
one.
okay, what are we trying to do first? What are we trying to do with this method?
Yeah. So the goal is you're going to receive a root, which can be any node technically. Okay. Any node in a binary tree. And the goal is to print all nodes after that node, all nodes connected to that node.
Okay.
To print their values to the terminal. Okay.
So we don't put the node because we don't want to print all the values of the tree.
Sorry?
We put the root. I'm saying we don't put the node in line 89. Q dot in Q.
Yeah.
We have a root inside.
I called it root. Yeah. Sorry. It's node. It's node. It's a root of some tree. Okay. It's a node.
Yeah. So what I'm thinking is, since we're not starting from the roots and we're starting, and it could be any node, it means that we don't have to pop the first node into the queue. So we need to find the node we're given, I guess. I don't know. Because I'm thinking we have a node that could be 5. 5 could be the root node. And then it could have 4 and 3 and 2. And so what if the node that was passed is 3? What if we're supposed, what if 3 was passed?
Yeah. If 3 was passed, it should print 3 and then 2.
And 2. Yeah, so that means there's no point passing 5 into the queue now, is there?
Well, no. In fact, there's no way you would know what comes before this node. So you can't even do that if you wanted. Can be any tree. Doesn't need to be this exact tree that we're on right now.
So this, you're saying this method doesn't start at the roots? Or it doesn't need to start at the root?
Technically, this is the root. That's what you get.
Okay, so it starts from whatever node that you're given.
Yeah, you don't see this.
Okay.
I guess the icon is like you don't see this, right? There is no way you know what comes before a certain node. There's no connection backwards, so you don't even need to think about that.
Yeah, that makes sense. Okay, so since we put in that in the queue, so we need to find a way to check to see that there's something in the queue. So while the queue is not empty, the first thing we'll do, right, is to dequeue the Q1 item from the queue. So
And place it where?
in a variable, I guess, of some sort.
But which one?
You're asking which variable?
Yes.
We can name it something current. Yeah.
Yeah, sorry, please. I'm kind of confused on something.
Yes.
Where have we defined the queue that is on line 87?
It's just a standard queue. Right. It just has like storage with a double linked list, a in queue with add to have, and
Okay, so we are importing it from here down to the other place.
yeah. I think I didn't import, but I can if you want.
Okay.
I'm gonna do it for the stack as well, since we're at it. Yeah. All right. So let me just go ahead. Where's the binary tree? Okay. Okay. So we have our queue.
Yes.
And we
So
dequeued something. So what's
we
next?
dequeued something. So what we want to do now is we want to check if whatever we dequeued is on the left. No, if whatever we dequeued has a left node, has something to the left of it.
Like this.
Yes. And if it doesn't, no, if it does, not if it doesn't. If it does, we want to push that thing into the queue. Okay. And yeah, check on the right as well.
Okay. So anything missing here? So the goal is to print.
Yeah, so want to print the value of the current node. So we could just print current value.
All right. Seems fine. Yeah, seems fine to me. Questions?
Okay, in line 92, in the while in the loop, is that correct? We are looping there. So
Yes.
there we are looping the if the length.
Yeah, so we're looping
The storage of the queue is greater than
while the
0.
queue has something inside. So this is, by the way, this queue here, I didn't add a self.size like you have it on your projects. Okay, so what I did instead was taking advantage that the storage is a doubly linked list, right? I went there and checked, and behold, and the list has the length, right? So we can use that to check if we have something in the queue. Okay, does that make sense?
Sorry, so in line 92, we're checking if something there is in the queue.
Yeah, exactly. So if the queue has more than 0 items in it, then we keep looping until it has nothing and we stop. Okay. Just a quick fix here, because it's not a fix, but it's kind of a preventing an error. You could just prevent that the case where the node is not valid, so just don't do stuff, right? But that's just a detail. So any question about this?
So what I'm struggling to understand now is on line 92 and 93, we are adding the node into, we are turning it into a queue, a node on a queue.
Mm-hmm.
And then immediately on line 96, we are decoding the node again. So
mm-hmm.
What's the point of adding it into like this data structure and immediately removing it just to print when you could have like just printed?
Yeah, so in fact, that's exactly what happens at the first time, right? The thing is that after the first time this loops, there's further nodes to discuss, which are the left and the right nodes of all the things that he finds, right? So this is kind of a push to get the loop started, okay? So it's kind of a let's start with the original node, right? And print that value out, and then we place in the queue all the left and right nodes. And then the loop keeps going up until a point where it doesn't find any other node. Okay. But yes, indeed, at the first time, what happens is the queue is starts with the original node, so the root node, I guess, and at the first time it will dequeue the exact same node and take care of it, because it will have to print its value, it will have to check the left and right, so the loop can continue and go throughout the whole tree. So it's a starting point here. Is that clear?
I'm just a bit confused about the difference between self and node.
The difference is this.
Like so far, we've always been sort of using self. Like I'm confused what node exactly is.
Yeah, I'm going to show you the difference. So self is my current node, okay? It's the node I called this function on. So if I had some node, I don't know, I created it somewhere and called BFT print on it. And we didn't have this, right? This is your node, right? And we could use the self instead of the node variable, okay? But the thing is that this BFT print is not trying to print the tree of itself. So what I mean by this is if I create a tree with this class and I had this method here without the node here, what it did is print the tree itself. So it would print the exact same tree that you're calling it from, okay? But here we're not using self, we're using node. So the reason we're using node is that we can call this on any other tree. Any other tree will work here. So using this variable here, basically we could print out any other tree with a breadth first style, okay? And that's the difference. So if you use self, you are restricted to printing the key that, sorry, you are restricted to printing the tree that you call it from. But if you use node, you can call any node on any tree and print out the rest of all the nodes below it.
So basically, if I'm kind of printing printing the whole tree that I'm currently on. I can just call, I can just pass in self as the node, right?
Sorry, I'm having trouble understanding. I don't know if it's your mic.
Hola, you are breaking we can hear what you're saying. You're breaking.
Maybe type out in the Zoom chat. We will be able to see. Okay. Let me just check. But yeah. All right. So, yeah, Olamide, just try to type it out in the Zoom chat, or yeah, just tag me somewhere in Slack. I'll be able to see it. But otherwise, was it clear, Owen?
Yeah, I kind of get it, but I think I'm just tired, to be honest. So,
just a review, right? If you have a tree here, 3, 1, okay, and I had another one here, so 3, 2. I could call sorry, that's not it. I could call n dot BFT, right? So I could call n.bft and send any node from this tree here. I could send any node from that tree because I have this argument, okay? So I could say like n2 and it would print out the whole n2 tree, okay? But if I didn't have this, you would have to call n2.bft to print itself.
So self is kind of a tree, not a node.
No, it is a node. It is a node, but our code goes through all the tree. So it self is a node. Don't get me wrong. So they're both nodes. Okay, both of these variables, you just get one node. Okay. The thing is that all of this code here, it keeps going forwards in the tree, level by level, right? Like I talked about before. All the nodes on that level will be printed out, and then the next level, and then the next level, right? So technically you receive just one, but all the further nodes down the tree will be printed, right? So the difference here with the self is that if you call it from some tree, some node, if you call it BFT, if you only had the self, it would print only the tree itself from this node. Okay, but with this argument, you can print other trees too. Okay, so it's basically to give it more functionality, allowing other trees to be printed with this method, and not only the tree itself. I hope that's the best I can do there with the explanation. Was that good enough? Yeah.
Yeah, thanks. So node is initialized at the start, is it?
Well,
no,
this is just an argument.
It's not.
Right.
Yeah.
It's just an argument. So it comes from outside. When you call it, let me just close this. Let me just see here.
And it's like an index. The node is like an array index.
Binary search 3. Okay. 3, 2. If I call 3.1 dot ft print, right? I can send 3.2 to print out, right? That's your node right now. This is 3.2 instead of just 3.1. Okay. So I can send this
But
node.
tree2 becomes self, not node, yeah?
No. Tree2.
Then what is self? Self is
Self
tree1.
is tree1. Exactly.
Right.
So again, like with any method inside a class, and this doesn't apply just to data structures. This is like Python basics. Okay, so with any class, you have the self, and the object that calls it is the self, right? The object that calls the method is tree1. You have the dot. The dot is the call, right? You're saying on this object call bfj print, and this is the self. Okay, this is like the context. This is your node that it comes from. Okay, so you're accessing this method from tree1, but you want to print tree2, right? And that's what this argument is for. It's to receive different trees and not only itself, because if I didn't have it, the only access I would have within this function is to my own tree, right? Is the only thing I would be able to do is this, okay? So with this access, with this new argument, we are able to print out other trees. Okay, so it's an extension.
It's more dynamic.
Yeah, it's like it's just more functionality present, right? And if you still
So
want
this is iterative because it's kind of, there's a loop inside it.
Yeah, it is iterative. So it's not calling itself. So yeah, indeed, it is iterative. Okay.
Cool. Thanks. Sorry about all the confusion. Thank you.
No problem. That's the goal here, clearing up stuff. So that's it for breadth first. Okay, so we have Olamide. If I plan on printing the whole tree, I can pass in self as the argument. Not really. So here you cannot pass self as the argument. It's automatically passed when you call it from somewhere. So this is your self on this function. So you cannot technically do this. This doesn't exist as you're not inside any class to use the self keyword. Okay. So
yeah. Okay, so I guess where the confusion was from, like when I was thinking about it, is why will I need to call tree1 if I want to print out tree2? But like thinking about it, say I need to like maybe use the values from tree2 in tree1 apart from just printing. So it actually makes sense that the method was written that way. So that's just how I've thought about it. I think I kind of get it now.
all right, so you got the difference. That's
Yeah.
what matters. All right, so yeah, good. So because we're kind of reaching the end of After Hours, I'm just gonna speed this up, right, and explain to you the contrast here with breadth first and depth first. The only difference now is what data structure you're using. Okay, so as you saw before when I explained how the queue worked in the stack with the tree, how it would print out, right? You saw that just by using the stack, it would print out the numbers in order from bottom up. It would print out 7, 8, 9, 10, right? And with the queue, it would print out level by level, so from top down, right? So the only difference here is doing this, right? I can just go select all of these methods and adapt them to use a stack instead of a queue, and I will have my depth first traversal working. Okay. The only difference is the data structure you use to process the data. and that changes the order that the nodes are printed out, because the data structures work differently when you add and remove stuff from them. Okay, so that's how depth first is done, right? It's just you switch the queue for a stack, and there you go. Okay, obviously you have to switch the methods because they're named differently, right? So enqueue goes into push because it's how you add stuff to the data structure, right? And pop matches with dequeue because it's how you remove. Okay, so hope that was clear enough. Is there any last minute questions before we finish off? We didn't have time for the code challenge, but I'll share the link with you, and you can take a stab at it. It's a bit more practice for you. So
Thanks, Malka.
Yeah, I hope tomorrow's sprints will be similar to what we've done.
Yeah, Melky, thanks very much for the hour that you spent for us. We are all the old men here. I'm not talking about you, Alex. I'm talking about myself.
All right, guys. So I think we could call it a day, and yeah, I don't know much about the sprints, but usually it's all about the week. So if you guys have your daily projects going, you'll be able to do it, I'm sure. Okay. So
Thanks, Malky.
yeah, I'll see you all tomorrow.
Yeah, thank you.
See you then.
Yeah, bye.